Hi.
Okay, so let's go. Can everyone see my screen?
Yes.
Okay, cool. Right, so I was saying we're gonna do a double session. So I'm gonna try to do 15 minutes, then 10 minutes break. So my goal for today is to build something like this, and let's see how far we get, which is a cellular automata computational model. It's a very basic computation, but at least it will help you have some sort of an idea what you can do with a type of generative code, okay? So we're gonna build it step by step. And if we don't finish today, we continue next week. Okay, so let's have a look what we have in here. So essentially, you let's run it again. Essentially, we have almost like a 3D printing technique, right? Where we go layer by layer, we add another layer, right? And the way the layer is computed takes into account what happened in the layer below, and uses a very simple set of rules that are coming from Conway's Game of Life. And Conway's Game of Life is a neighborhood-based computation where you have some rules for cells that are either alive or dead. And there are usually 3 rules. So you become dead when you have more than a number of neighbors. You stay alive if you have a number of neighbors, and a new cell is born or becomes alive if there are a number of neighbors alive around it. Okay. All right. So let's start to build this. So the first thing we're going to need is some type of a unit that we're going to use to compute the cell itself, right? And I'm gonna go and create myself a 3D object, a cube, and let's place this in the origin. Okay. And now you can call this cell. You can call cellular automata cell. I'm just going to call it cell. And yes, it's a cube, so we know that. Now, I'm going to try to optimize it. So I'm going to remove quite a few things from this one. So I'm going to remove the box collider. I don't really need it. I don't need any physics. I think ideally we should have a material, not to have the default material. So that would be something good to create. Let's just make that now. Um, okay, and I'm going to assign that cell material to my material. Instead of the default shader, I'm going to use my cell material. And now we want to sort of give it a few, well, behaviors, functions, right? So to do that, I'm going to make a new script. And yeah, let's create in here a new C# script. And this is cellular automata cell. Okay. And with our cell selected, come on, show me its properties. What else happening? Hello. That's funny. I don't get my properties. Okay. Let's do the other way. So I'm gonna get this CA cell. Come on. Okay, now it's back to normal. So I'm gonna get the CA cell script that I made and drag these onto our object until you see this sort of blue line. And now I've attached the script to this. Okay. I'm gonna open this, and we're gonna start to write a few behaviors for this. And for this, I'm gonna see side by side the previous code um, to see what we want to have in here. So as with anything, you know that whenever you create a new script, you have by default the start and update function. So we're going to keep the update function, but we're going to get rid of the update of the start function. Now, we do want a few variables for this cell. And I think because we know this cell is going to have an alive and a dead state, we need to somehow store that information. And we're going to do this with an integer. And we're going to assume 0 is dead and 1 is alive. Okay? So that's the assumption, that if a cell has state set to 1, it's alive. If it has state set to 0, it's dead. Okay? Now, because this cell can also become alive, so based on how many alive neighbors it has around, it can become alive in the future. We also need to somehow track this. And again, we're going to initialize this value to 0 to assume that even in the future the cell is still dead. And again, probably to keep track, if we've in a grid of cells we have computed one cell, we might want to track this. So we're going to use Boolean, and we're gonna set this to false. Okay, now let's go and write ourselves the behaviors. Okay, so we're gonna have some behaviors or functions of the cell, right? All right, so a few of them are just very simple ones. So I want to be able to set these variables, right? So all these variables that I've made, I want to have certain functions that I can access from outside the cell itself by another script. So for example, one very simple one would be to set the computed. So if I've computed one, I want to do that. And we're going to use a Boolean. Okay. And this is very simple. The variable that we're passing in the function, we're going to store it in the local variable. So we're going to say computed is equal to underscore computed. And remember when I was telling you about writing code, a variable that you're going to pass from the exterior of the function is usually good to have it with this underscore to showcase to other people who are reading your code that this is something that is passed or given from outside the actual script itself. Okay. Now we will also have a few behaviors. So for example, one that we will want to do is how we display this cell. And let's call this display cube, why not? Or display cell, because we called it. Okay, now the key thing for this is we want to optimize. So we know we're going to use a grid of cells, and it can get quite big. So for example, if you use something like 40 cells by 40, that's already 160 cells in one layer. And if you multiply that by, let's say, 100 layers, you get 1,600 cells. So it's quite important that we optimize how we display these cells. And the best optimization is to group them, to say, well, I want all of them to be displayed the same. Why not? So then I can set properties for one, and all the cells inherit the same property, which means in having to display them, the video card will just go and pick up the property of one and apply it to everything, okay? So for that, we're going to use something called a material property block. Okay? And not with caps lock, let's call this props. And this will be a new material property block. Let me make this a bit bigger so you see what I'm doing. So I'm creating a material property block. I'm giving the name props, and I'm initializing that using the material property block function. Okay. Now I do want to apply these properties to the actual material that is attached to the object, right? And if we go to Unity, we can see the material lives under the mesh renderer, right? So the mesh renderer contains the material, and the cell material, if I select it itself, you see it has a set of properties, right? The color, the shading, so on and so forth. So what we're going to do, and again, some things that I can already do. So to make it quite fast, I'm gonna set the properties as a block and then apply to everything. Okay, so because we need the material itself from the mesh renderer, it's a good idea to just get the mesh renderer and save it. Okay, so to do that, let's declare it locally. So we're going to need a connection to our mesh renderer, and we're gonna call this the renderer. And then some very simple functions that we have to go with. So the simple one, we're going to ask if a cell is alive or not. So for example, if a cell is dead, then I don't have to do anything to it because the mesh renderer is hidden, right? If a cell is alive, then we're gonna set the property, okay? So let's ask, what's the state? Okay, so we can actually say, if cell is dead, then ignore. So we're going to ask, is the cell dead? And what we're going to do, then ignore it. Instead of then ignore it, then hide it. So we're going to go to game object, get components, and the type of component we want is the mesh renderer, right? Okay, so, and then we're going to say that it's disabled. Okay, let's make this a lot bigger so you can see the whole line. So if the cell is dead, we hide it, right? So we get the mesh renderer, and we say that is hidden. So this is equivalent to me going into Unity and basically getting my cell, getting the mesh renderer, and you see the enabled, setting it to false. So essentially, we're hiding it. We're not deleting. It's still in the game. We still have it in the hierarchy. It's just we have hidden the mesh itself. So it's a very clever way because we know in the future it could become alive, so we don't want to delete it. Okay. Now let's go back to the code, and we're gonna write the next part. So if it's alive, if cell is alive, show it and set the property, right? Okay, so very similar to this part, we're gonna get the game object, but instead of saying that is enabled is equal to false, we're going to say it's equal to true, right? So this shows the object, okay? So the next part is to set the properties. Okay, so let's go to the props. And the thing we want to set is probably the color. Okay. And in here, so the color, if you look at it, so if I go into Unity, the color, if I select the material, you see it's set under the albedo, right? And the property itself, and again, this is something specific from Unity, it's literally called color. So we need to actually call it, right? Oops. So in the set color, in the color property, we need to put an actual color. And up to you what color you want to use. I used black, but you can use any color you want for your object. Okay. So for the props, we set the color, right? That's the function. And the property is called underscore color. And we're using a default Unity color black, but you can use any color you want. You can even set a custom RGB, right, if you want. Okay, now with that being done, I haven't actually applied it to the mesh renderer, right? This is just the property. I've set the property, but I now need to actually set it to my renderer. To do that, I'm going to get the renderer, the one that I defined here, and I'm going to make a link to my game object mesh renderer, right? Okay, so my renderer, the one that I defined a bit earlier, remember we defined it, the mesh renderer. I now link it to my game object. And I say, hey, game object, get component the mesh renderer. Now that I have the renderer itself, I can set the properties. And I can go and call the set property block. And in here, I need to pass what properties I want, which is the props. Okay. Now, in all fairness, we can do more to the props. So you can also set other things if you want, like the texture. And again, quite a bit of things you can do with that. But for us, is the color that we care about. Okay, so with that, oops, we're sort of finished with the display cell function. Okay, we do have a few more functions that are, again, helpers. So function to set the feature. So we need a function to set the future state from outside the script. And because we want this to be accessible from outside, it needs to be public. And we're going to say it's a void function. And again, because we know the future state is a Boolean, we need to pass in a future state Boolean, right? Sorry, it's an integer. And this is a very basic function. Future state will be equal to, let's call future state. Now, in all fairness, set state, I don't think I ever use it. So we won't do that. But same as setting the future state, I might also want to get the current state, okay? Okay, so again, this is going to be a public function, void get state. And actually, it's not the void function because we actually want to get the state. So remember, the state is an integer. So this one will just return state. Okay. Again, get future state. I don't think I'm ever going to use it. And in all fairness, I'm not going to use the rotate cube either. So let's keep it simple. So essentially, my functions, behaviors, are the set computed, display cell, and set future state and get state. Okay. Now in the update, we're gonna do a bit of work. So we're going to ask um, if the cell hasn't been computed yet, right? So if we're still to compute the state, then we need to say that the current state will become the future state, right? And we're going to display the cell, okay? Else, if it has been computed, right? We're just going to display the cell, okay? So very simple update. We're just asking, is the cell still being computed? If yes, then we're going to set the state to future state. At that point, we're gonna assume we finish computing and we just display. Okay, so quite a nice function. So we have now a little cube that has a few properties and has a few behaviors. And the behaviors are very simple. Basically, get displayed as a black cube if it's alive, and is not displayed at all if it's dead, and has the capacity um, from frame to frame to keep in memory if it is alive or if it's dead, right? So it's a very simple cube with memory and the ability to show and hide itself, okay? Now, we're gonna save this as a prefab. Let's call it CA cell. So we can use this as a prefab. So if you want to make a prefab, you just drag it from your hierarchy to your assets. Oops, I've made two of them now. I don't want two, I want just one. Now that it's a prefab, it means that I can just grab it from my asset and I can make a bunch of copies and all of them would have the same thing. Now, if I want to edit the prefab, I can go in the prefab itself, right? So for example, maybe one thing I want to change, as I was saying, maybe the color is black. Cool. And I'm gonna take out the smoothness to make it quite fast to compute. And now that I'm happy with this, I can exit my prefab and all of them have been updated. Good. So that works quite well. All right. Now, I'm gonna delete all these guys. And I do want something like this. I want to make a grid of these cells, okay? So for now, I'm going to disable this, and I'm gonna make one from scratch. So what I'm going to do, I'm going to create an empty game object. and let's place it in the origin. And let's name this as CA grid. So this is going to be where I'm going to compute all of my cells. Okay. Now, I do want something similar to this. And to do that, again, let's make a new script. Okay, so in here, I'm running out of names because I keep doing this example. Let's call it, why not? Let's call it CA grid. So we're gonna make a new C# script. Let's call this one CA grid. Okay, right. Let's select our CA grid. And again, let's wait for this to update. Okay. And I'm going to get the CA grid script and attach it to this. Okay. All right. Boom. So let's start with what variables we need. Well, I think let's first define how big the grid is, right? So let's say number of grid columns. So how many columns we want? Let's set it as 40 initially. Then, to be fair, it's very long, so let's just call these columns. Then we're gonna say how many rows we want. And then we're going to say how high we want this grid to be. And yeah, let's give it a nice proportion. So it's twice the height than the width. Okay. So let's see how this works. And definitely at this point, because our grid is going to be made of the cells, we want to make a reference to our actual GUM cell prefab. So let's also declare that. So that's a game object. Okay. So let's go to Unity. If this updates, we should have also in here, yes, the CA cell prefab. And again, probably to make it simpler, it should just be called a cell prefab because that's what it is. So let's just call it a cell prefab for the simplicity of it. Okay, now we have to link in the actual prefab. It's not yet linked in. So I'm going to go to my prefabs and get the CA cell and drag it in here. Now I've made the link between my script and the prefab itself. Great. And at this point, we're ready to continue with the script. Okay, so what else do we need as variables? Right, so let's call these okay, so those are variables to set up the grid. Then we need some variables to save the grid data. So for that, This is going to be internal. We're going to use an array of cells to store the layer. Okay, and then we're going to use a double array which is going to be a stack. Okay, so let me show you what that means. So for now, I'm gonna disable this guy. And enable the old one. And let's allow it to compute to see what's happening in here. Okay, so you see how the layers are being computed, right? So what we're doing each frame, we're computing a new layer, right? So for example, if I get layer 0 is this one, layer 1 is this one. And if I want to get one of the top layers is this guy, right? And essentially what we're doing for each layer, we have the same amount of cells, the 40 by 40, right? And in the cells themselves, we're keeping in the alive ones with the mesh renderer turned on. So if I expand the layer, you see in here I have all these little cubes, right? That I'm using in my layer. So you have to think of the stack being made of all the layers. So if I would have the whole stack, it would be made of all these layers, and each layer is made of cells. Okay? Cool. So let's go back to our script. Let's enable this guy. By the way, let's save our scene as well. Okay, so now let's go back to our script. Right, now what we want, we probably also want to keep a track of how high this layer is being computed. So we're going to use a local variable. Let's call it current height. Current height. And obviously when it starts is 0 because it starts at the bottom. I think we also can do something about how we want to space the cells. So for example, if we want the cells, instead of being linked to each other, we want to space them a bit, we can give the spacing more than 1, and it will just space them a bit. Okay. We probably want to also keep track of how many cells are alive. So this is going to keep track across the whole stack how many cells we have alive. Okay. Then I think, yes, also this is a good idea. So one thing that we want to control is how the grid starts, right? So the initial layer where we place the initial cells, I think we should control. And we can do that by giving an image, and that image can be sort of the starting frame. So instead of having randomly generated some cells on the grid, we can draw them in something like Photoshop, and we can set what's the initial start of the simulation, okay? And we can do that with a texture. And let's use a texture 2D, and we're going to call this the seed image. Okay, let me show you what I mean by that. So if I would go in my In here, I have a few images made. Okay, so let's see how this looks as an actual image. So essentially what I did in Photoshop, I created a 40 by 40 pixel image. And in this one, I sort of paint, and you can decide if, for example, uh, with white, you can represent cells that are alive, and with black, cells that are dead. So for example, if I want my grid to start with this pattern, with let's say 6 points connected by lines, I can sort of go in Photoshop and paint myself this pattern. I can also flip the pattern, right? So I can start with a bunch of cells that are alive around this pattern. And up to you to create compelling images, right? What's important, just remember the seed image has to be the size of your grid. So if you're using a grid that's 100 by 100, in Photoshop you have to make a 100 by 100 image. And then with the brush, you can paint the pixels. Okay, so I'm gonna go in here and link in my one of these seed images. You can make yourself any image you want. What's quite important, whenever you import an image that you want to use as texture, you need to change its texture type to be a sprite 2D or user interface, okay? So that's quite important. You have to say that, hey, this is going to be um, a texture 2D, otherwise it won't be recognized. Okay, cool. So I assume you guys don't have this type of image. So what I'm going to do, I'm going to share it now on the chat, so you can also import the same image. Cool. So you can save it and use the same image as I'm using. Okay, cool. Now let's go back to our script. So we sort of have almost everything we need. We do need to somehow control the computation variables. Or computation rules. Right? So we know we have 3 rules. And because we want to control them from the outside the script, let's make them public. So when a cell dies from overpopulation, and let's use Conway's initial rules. So for him, if you had more than 3 neighbors, you died. And then staying alive, for him was 2. So if you had just 2 neighbors around you, you stay alive. And if you are dead, so these 2 rules are for alive. And if you are dead, you become alive if you have around you 2 cells, right? Okay, so now we have that plugged in as well. Okay. So now let's go into the start function. So the first thing we want is to initialize our stack, okay? So we don't have yet the stack object, right? So what we need to do is to actually make it. So we're going to say that the stack will be equal to a new game object. And we know this is a double array. And we need to say how many objects are in here. So for here, we were going to use the, I think I'm using columns, row, and height, yeah. So we're going to make it the size of our columns, rows, and height. Okay? Cool. So we have now initialized the stack as a data structure, right? So this is a double array. So it means we can store on 2D and also 3D. Now, at this point, we want to call a function. And actually, instead of calling create layer, let's call this create initial layer, create start layer. So this is the layer at the bottom, right? The first one that starts the computation, okay? Now, let's go and write this function. So the first function we want, and this is private, and it's a void function. Okay. So what do we want to do in the star layer? Well, we're going to use our seed image to populate that grid. Okay. Okay. Not update. So here I'm looking for the yeah, let's do like this. Yeah, so let's do like this. So the first step, step one, we're just going to create the layer itself. Okay, so for this, we know that the layer, the one that we set up, is going to be a new game object array. Oops. And we know this is the size of columns and rows, right? So we know our layer is the depth of columns multiplied by the number of rows, okay? Then we need to actually populate the layer with some alive cells, okay? So we're going to go in the layer, and in each cell, we're going to put one of these alive cells. For that, we're going to use two for loops. So we're going to start at counting as 0. I will be smaller than the number of columns, and it's going to increment with the step of 1. Then we're going to use another for loop that starts at 0 and stops at the number of rows. Okay, so what we want to do here, we're going to initialize one of our cells based on the seed image, right? So to initialize one of our cells, what do we need? Well, we need the position of the cell in space, we need the rotation of the cell in space, and we need the state based on the seed image, right? Okay, so for the position, we're going to use the vector 3. And this is going to be a new vector 3. And where are we? Well, we are at position y that we want to multiply by our spacing. Correct? Then probably for the height, because this is layer 0, right? We can actually use the current height, right? Because the current height is already 0, right? Because we started, so we haven't actually increased it. And then we want j multiply by spacing. And here I have a bit too many commas. So let me make this quite big so you can see it. Okay? So the cell position, it is the I counting multiplied by the spacing. Then the current height, which is 0, because it's the first layer. Then j multiplied by spacing. Okay? So you're going to imagine as I increases becomes 1. So the first one starts at 0, then 1, then 2, then 3, so on and so forth. And then it goes 1, 0 again for I, but j increases. So we sort of populate the grid one by one. Okay, next, we want the rotation. And for this, we're going to use the quaternions. And we're going to say it's not rotated. So we're going to use the identity. Okay? Cool. And at this point, we have enough data to create the cell. So we're going to say game object, new cell, is going to be instantiated. What are we instantiating is the cell prefab, right? Where are we instantiating the cell prefab? At the cell position. Then using the cell rotation, okay? So at this point, we've made a new cell by copying the cell prefab and positioning that prefab at the cell position with the cell rotation. So that's quite good, but remember, we want these cells to be a child of the layer. So what we're going to do, the new cell, the transform, and the parent is going to be the current game object transform, which is the CA grid. So it's going to be this game object transform. Okay? Cool. So we're almost done with this. We have to set the state. So now we've copied the cell, but we haven't actually set the state yet. So we need that information. And that is going to be read from the seed image. And to read from the seed image, So we're going to get an integer and seed image, and from the set image get, and I think we want to get pixel, yeah. So we want to get the pixel that is at position I and j, but that pixel usually comes in RGB values, so we want to transform that to grayscale. Okay? So let's see that a bit bigger. So we are reading the cell state from the set seed image by getting the pixel that is stored at the position where the counting happens, right? So if I look at my seed image, if I still have it open, no, I don't have it open anymore. So essentially, imagine our counting starts somewhere here, 0, 0, and we go read that cell information. At some point, I'm going to be I equals to, I don't know, maybe 5, j equals to 5, and I'm going to read somewhere here. And when I'm here is 40 and 40, right? I equals to 40, j equals to 40. Cool. We're almost done. So we've read this new cell state, but we also have to compute it at this point. So yes, from the new cell, we want to get the component. And remember, the script we made was called CA underscore cell, right? And the function we want from this is the we haven't yet written the function. So let's go back to here. We've done the set future state, but we also need the function to set the current state. So it's going to be called set state. And in here, state is going to be equal to underscore state. And by the way, if you didn't follow along, I'm just going to send you after the class all the scripts, so you have exactly the same thing I have, okay? All right, we're almost done. CA grid in here. We want to set the state, and what is the state is the new cell state. Okay. One more thing. We actually need to save this in our data. So in here, we want to actually save this new cell. And with that, we are actually done. Yeah, cool. Let's see if this works. And then we take a 10-minute break. Okay, so I have my CA grid that has a seed image. And it should be that when we go and play the game, we should get one. Well, it's out of the view. Oh, what happened? Are they all dead? Apparently, I got all my cells dead. They are there. Just they're all dead. Quite funny. Okay, it's working, but for some reason they're all dead. So I might need to have a double look at what happened with the seed image, but it's working. So we're getting the initial um, layer. Okay, let's take 10 minutes break and we'll continue at 9:10, if that's okay. So far confusing what I'm doing, or it feels like, oh, okay, we understand what's happening in here. Yes, not confusing. Okay, cool. Uh, right, okay, let's continue in 10 minutes then. Cool. Let's continue, okay? All right. Let's see what I'm doing wrong with the set state. I think there's something I'm not doing right. Okay, you keep state. Oh, I know what I'm doing wrong. I'm not updating. Okay, so they are actually done correctly, but we actually have to call the display um, yeah, in the update function. Yeah. Okay, but let's continue. So we have now a function that creates our layers. So we have to actually think how we're going to do the update, right? So in the update, what we want to check, um, we want to check if our stack has grown to the height we set up in the beginning. So the first thing we're going to ask is what the height of the stack. Okay, so if current height is smaller than the height we set out in the beginning of our computation, we're just going to update the current layer. So we have one layer that we've computed, so we want to update it. And then after we've updated the layer, so basically went through the cells and make sure that the next layer is computed, the one above, we also want to probably save it. So yeah. So that's the first thing we want to do. And the next thing we want to save the current layer to the stack, which we're going to do with a save layer function. And because we want to make sure that at some point the computation stops, we're going to just increase the current height, right? All right, now we have two functions that we have to describe. So the first one is going to be this update layer function. Okay, and again, this is a private function. Okay, and so this is a function to display the current layer and compute the next layer. Okay. And we know we also want the other function. So we want the function to save the current layer to the stack. And again, this is going to be a private function, void save layer. So I've made myself the function so I don't get some errors, right? Because the function doesn't exist. All right. All right, all right, all right. Okay, so the first thing we're going to do, we're going to assume all the cells are dead. So we're just going to say that alive is equal to 0. Correct? Now, we need to go to the layers that we have, right? The layer that we're computing, and get the cell state, right? So go to the layer and okay, so we go to the current layer and we compute the next layer. And again, we're going to use our two for loops. Okay, so the first for loop is going to go through the columns. Then we have the second loop that goes to the rows. Okay. So we're gonna get a current cube, okay? Or current set. So for that, we need a game object. The current cell is going to be equal to the layer I and j, right? I'm missing here the j, right? Then we actually want to get the state of the current cell. And this, we're going to use the function we created. So from the current cell, we want to get component. And the component we want is the CA cell. And from the CA cell, we want to get the state. Let me maximize this so you see it. Okay, so from the current cell, we get the CA cell component, right? And we know that the CA cell has the get state function. So that returns to us the current cell state. Okay. Right. Now that we know the current state, we will need to compute how many layers, how many neighbors are alive. And again, we're going to assume that none of around me, all the cells are dead. So I'm going to start with the assumptions that there are no alive cells around me. Okay. And as we compute how many alive neighbors are around me, I'm also going to compute the future state of my cell, right? And again, I'm going to assume that the worst case scenario, you're dead. So I'm gonna start with the assumption that in the future, the cell is going to be dead. So this is going to be dead. All right, now this is where maybe we need a bit of Photoshop to explain things. Because it's quite easy to see how many neighbors are around in a cell that's in the center of the grid, but it's also quite important to look at edge cases, the ones that are on the margins, okay? And let me explain this. All right, so let's draw a grid. So I am going to sort of assume I have something that looks similar to this, right? Well, almost equal. Okay. So I'm going to sort of, let's draw the cell as being ellipse, right? Okay. So let's assume I have a few of these cells alive. Let's say something like this. I guess let's put one here. So that's my layer. And in my layer, I have a few cells that are um, alive. Now, let's also put the indexes of all these cells. So I'm gonna get myself the text tool and somewhere here, I equals 0, j equals 0. And let's make it slightly smaller. And also let's set it to red or something like that so it's easy to see. So that's I0, j equals 0. Oh, come on. I want just the text. I'll select. So that's I equals 0, j equals 1. Let's just change this. J equals 2. Equals 3. Okay, then let's get all of these guys. Let's copy them. Here, so what changes? Here I becomes 1, j 0, okay, you get the idea, right? So if I would copy all these, the last one at the bottom, this would be I equals 3, j equals 3, right? So that would be the corner. So the start is 0, 0, the corner 3, 3. Now, if I have to calculate how many neighbors are alive, so for example, let's get this one. That is, at this point, it's a dead cell, right? So I could assume based on the neighborhood conditions. So remember in the game of life, if I have more than 2 cells alive, and in this case, if I look around the cell, so I have 9 neighbors, right? 8 neighbors, sorry. 3, 5, 7, 8. So I have 8 neighbors, and I go, okay, top left, I have 1 that's alive. Top above, dead. Right above, dead. Left, dead. Right, alive. Top bottom, dead. Sorry, bottom left, dead. Bottom alive. Bottom right, alive. So this cell has around 1, 2, 3, 4 cells. So in the future state, it will become alive because it has enough neighbors to become alive. Now, for example, let's take this cell, right? So let's see how many neighbors this one has. This one is what I call an edge condition. So basically, he has just 3 neighbors, right? So for him, based on the conditions, I see none of the cells are alive. So in the next state, he will become dead, right? Now let's look at some of the other ones. So now let's take this guy. This guy has actually 1, 2, 3, 4, 5 neighbors, right? So he's an edge condition as well. So for the edges, we have corners that have 3 neighbors, right? So this corner has also 3 neighbors. And we have edge conditions that usually have 5 neighbors. So this guy has 5 neighbors, this guy has 5 neighbors. Also, this guy has 5 neighbors, right? So I have to sort of go through my grid and deal with the cases that are in the field. So this one is a field condition. He has 8 neighbors. And then I have to deal with the cases that are on the top edge, bottom edge, left edge, and right edge. Okay? I also have to deal with the ones that are on the corner, right? The top corner, top left, top right, bottom left. So I have to kind of write a lot of if statements. So bear with me on this one. So the simple one is for cells that are not on the edges. Okay? So that's simple. If I is bigger than 0, right? And I is smaller than columns. But in reality, it's columns minus 1 because you know how computers count. They start from 0, and if you say you want 40, they count to 39, right? Okay, so that deals with the I. So the ones that are in this direction, right? Correct? So I bigger than 0, so that's 1, but smaller than 3. So pretty much this. I also have to deal with the J's, right? Okay? And then we say and J should be bigger than 0, and J should be smaller than rows. Okay, so these are pretty much the cells that are in the field. So they're bigger than 0 and smaller than columns, bigger than 0 and smaller than rows. And again, it's rows minus 1. Okay, now I sort of have to go and get all the 8 neighbors. Remember? Right? So I have to get the current neighbor state. And if the current neighbor state is equal to 1, I increase the number of alive neighbors, right? So that's what I want to do. For each cell, I want to count how many neighbors are around. So for this, we're going to ask if, and the way we're going to get it is quite simple. We're going to get from the layer, we're going to get the 8 ones. So we're first going to go layer I minus 1, j minus 1. Okay? And from the layer itself, we know we now got the cell, but we want from the cell to get the component, and the type of component is CA cell, right? And from this one, we want to get state. And if the state is equal to 1, right? If that actual cell is alive, then I'm going to say that alive neighbors increases, right? And let's make this really big so you can see this. I don't think I have enough screen space. Almost. Okay, so that's the top left. So let's go to Photoshop. So what I'm doing for this guy, I'm first getting, let's draw it with a line. And the line, let's make it red. So I'm getting this one. Let's make it maybe thicker. Oh, I don't think he drew it. Anyway, you get the idea. I'm getting the I minus 1, J minus 1, right? Because I'm, look at 1, 1, I minus 1, J minus 1 gets me this corner. Then the top one is I minus 1, J. Then the top right is I minus 1, J plus 1, correct? So let's go and write those as well. So that's the, if it's easier, I can write. So this is top left bar. Then make my life a bit easy, I'm just gonna copy this top bar. So that one is just J, correct? Then what we want, top right neighbor. So that's I minus 1, and this is changing to J plus 1. Okay. And I will continue in the same fashion. So then I want to get uh, the neighbor to my left and the neighbor to my right. So how we do that? So the left neighbor is going to be I minus 1. And here, sorry, it's just I and J minus 1. So that's the left neighbor. And then I want the right neighbor is J plus 1. So that will be J plus 1. Cool. Now I have 3 more neighbors to get. So first the bottom left neighbor. So that would be I plus 1, J minus 1. Then so the next one is the one that is just below. So I plus 1 and J. And the last one is the bottom right. So that one is I plus 1, J plus 1. Cool. So that sort of solves my neighbors if I am one of the cells that is in a field, right? So if I'm one of these cells that's in the field, that deals with that. But obviously, I have a bunch of edge cases. So let's deal with the next edge cases. Okay, so for cells that are not edges, And that's easy. Okay, so for this one, we're going to ask if I is bigger than 0, right? Um, sorry, if I is 0, so for this are top edge. So for the ones that are on the top edge. So for this one, I will be equal to 0. And I is smaller than columns minus 1, right? And j should be bigger than 0 and j smaller than rows. And sorry, I smaller than columns minus 1. Yep. And here, smaller. I'm always getting confused with this. Okay, and j should be j bigger than 0 and j smaller than rows minus 1. I hope I got this right. Yeah, smaller than rows minus 1. Okay, so it's very similar to what we did, but in this case, we obviously don't have neighbors that are on the top, right? Because I'm the top edge. So for this one, because I don't have any of the top neighbors, I can just go and calculate left neighbor, right neighbor, bottom left, bottom, and bottom right, correct? So I can copy all of this. I can go in here, paste it. So I have a left neighbor, a right neighbor, bottom left, bottom neighbor, bottom right. Okay, so that deals with the top edge. Then we have to deal probably left edge, right? Okay. Okay, so the left edge should be that I is bigger than 0 and I is more than columns minus 1, and then j should be precisely 0, right? So if I is bigger than 0, right? And I smaller than columns minus 1, and j is precisely 0, and j is bigger than rows minus 1. Let me see. Smaller. Sorry. Jesus, I'm always getting confused. Okay, so basically, this is where it becomes a bit funky because, so I'm on the left edge, so I want to check everything to my right. Okay, so I pretty much, I think the easiest way is to just copy everything and then delete everything that is to my, so because I'm doing the left edge, I'm gonna delete everything that's on my left. No checks for left. Okay, so let's just copy all of these guys. And then we're just gonna delete the ones we shouldn't check. Okay, so I can't check anything on the left. So this one is out. Top neighbor, yes. Top right, yes. Left neighbor, no. So this one is out. Right neighbor, yes. Bottom left, no. Okay, so bottom neighbor and bottom right neighbor. Okay, so I've dealt with the left edge. So I've done the top edge and the left edge. Now I have to do the right edge and then the bottom edge. Right. Okay, so what does it mean that they're on the right edge? So I should be bigger than 0, and I should be smaller than columns minus 1, and J should be bigger than 0, and J should be perfectly equal to rows minus 1. Okay, so those are the ones. When J is equal to rows minus 1, we're on the right edge. And again, I'm gonna double check against the other code to make sure that, yeah. Oh, J equals to rows, exactly, because in this case, we are on the edge. All right, so again, the easiest way to do this is to just copy the 8 neighbors and then delete everything that's on the right. So top left is okay, top neighbor, top right we can't do, right? Because we're on the right edge. Okay. Left neighbor, then again, this is something we can't do, the right neighbor. Bottom left is right, bottom neighbor, but we can't do bottom right neighbor. Okay, so with this, we have finalized the cells that are on the right edge, and we have just one more edge to do. So the cells that are on the bottom edge. So for this, I should be bigger than 0, and I equals to columns. Right, so the cells that are on the bottom, and J should be bigger than 0, 1, and J smaller than rows minus 1. Cool. So that means I need to take out everything that's on my top. Okay? I hope I got this right, but we'll see. If something doesn't work, it's going to be very obvious. I think I did it wrong. So look, cells that are on the top edge. Yeah, I did it correct. Okay, I think, let's see. So on the bottom edge, I shouldn't check for things that are under my bottom because they wouldn't exist. So everything that is bottom will be out. Top, top, top. And I think this is Yeah, that's correct. So here I took out the top. So here I'm checking the bottom, and in here I'm checking the top. Cool. All right. And with this, we finalize calculating how many alive neighbors we have. Okay? So now I know how many alive neighbors I have, but that's not all. I need to actually do something about it, right? Cool. Now that we know how many cells are alive, I can go and apply the rules, right? So step one, um, where am I? Oh, I've done this in the save layer. Uh, sorry, this should have been done in update layer. Yep, sorry about that. Just change the names around. So I'm gonna get all this code. I think it's just easier to change the function name. So this needs to be the update layer, and this will be the save layer. Okay. All right. So step one, compute how many neighbors are alive. Then after we finalize the step one, we want to get into step two, apply the Conway rules. Okay? Okay, so first, rules for alive cells, right? So I'm going to ask if current cell state is equal to 1, so this is basically an alive cell, right? And remember, we computed here current cell state. Okay? All right, so check how many neighbors to see if it's alive. So we're going to ask if neighbor count alive neighbors is bigger than the correct population, overpopulation, right? Then overpopulation. Then what is going to happen? We're going to kill the cell, right? Let me see if I'm checking that first as well in here. Okay, yeah. So if it's bigger, then what we're going to go and say the current layer get component, and the component we want is CA cell. is going to die. Okay? Now, if it's precisely, and I think the one we're doing, yeah, so if it's exactly correct population, then he stays alive. Okay. So in here, this one dies of over. And the last one is that it dies of loneliness. Basically, it doesn't have enough alive neighbors. If alive neighbors is smaller than correct population, then he dies. So your chances of living are quite small because you die if you don't have the right amount of population, and you die if there are too many. But what's nice, um, we do have rules for cells that are dead, right? So rules for, so if the current cell state is 0, so basically it's dead, then for this one it's actually just one rule, right? If alive neighbors is equal to birth population. Oh my god, I misspelled it, birth population. Okay, this should be birth population. Okay. Oops. Going here. If let's do birth then is becoming alive. Okay, so actually in all of this is set future state. Correct, not the current state. All right, so that is updating the layers. Cool. Now it's actually quite cool to run the function as it is, because then you get the 2D game of life, which actually looks quite cool as well. But you're gonna get it in height. So he's complaining that the safe layer is not there, but it is there. I did make the headed void. Because it's with a capital. Okay. Save layer. Okay, I shouldn't have any more errors. Let's put the console here. Okay, cool. So let's see this. We should get the layers computed, but without saving them, if we did things right. There we go. So it's a 2D computation of the game of life, right? So we're computing each layer, but we're not saving the layer, right? It just goes in 2D, right? So it computes and then it stops. So that's quite cool, because if you ever want to see the game of life in 2D without saving the layers, that's sort of how it goes. And for this, to make it a bit more interesting, I'll give it maybe more frames, so you can see this over a bit more time. Okay, so it keeps computing, and after 200 frames, it should stop at some point. Okay, so it stopped. Perfect. I think we're again at the 1 hour mark, so I'm gonna stop here. And then let's again take 10 minutes break, and then we'll continue with the last part, which is going to be to save the layer. And basically what we're going to do, we're just gonna compute the layer, then save it on top and move the current computation on top of what we've already saved. Okay? Cool. Not a lot more to do. Okay, let's continue with the last part. We don't have that much to do, so we might even get faster than 3 hours. All right, so we're now computing the layers, but we also would like to save them. So for that, we're going to write a save layer function. And it's actually quite simple, the save layer function. It just goes to the current layer. Um, and what we will do, we will save that into the hierarchy, right? So um, I think actually to make things a bit easier, we're also going to make that layer part of the grid. Okay, cool. So the first thing we want is to give the layer a name. So the string we're going to use is a layer name, and this is going to be called, well, obviously layer, and we're going to attach to it the current height. And we need to, actually, I think we need to convert that to a string, yes. Okay, because it's an integer, remember? All right. Then we're going to make a new game object. And this is going to be a new game object, and we are going to pass in there the layer name. How do we call this? Oh, this should be underscore layer name. And to make things a bit more tidy, because I saw in the other one was not that tidy, I'm going to say the current layer transform parent is going to be this dot game object dot transform. All right. Okay. So essentially, we want to make sure that the current layer is a child of the CA grid. I saw in the previous computation I was not doing that, and I think it just makes it a bit cleaner. Um, and I should have done that also in the create layer, to be honest. Yeah. Well, we're going to save that a bit later. Okay, so again, we need our two for loops to copy. So here, let's just put a comment, create a new layer where we save the cells. Then go to so we're gonna go to the current cells and we will copy them to the current layer. So to do that, our two for loops, integer I is going to be 0, I is more than columns, I plus plus. Then integer j is 0, j smaller than rows, j plus plus. All right. And very similarly, we need to make a computed cell. This is going to be going to be the layer I and J. Okay, then remember we need a position and we need also the rotation. So vector 3 computed cell position. The difference is going to be that instead of 0, we're going to use the current height, right? And we should multiply it by the spacing. So this is an error here in this one. So this is going to be a new vector 3. So it's I times spacing, then current height times spacing, then J times spacing. Okay, let me make this a bit bigger so you can see everything that I wrote in here. Quite large, so I'm not sure it fits the whole. But we're doing a cell position that is I, height, J. Then we want rotation. And again, we're going to just use the quaternion identity because we don't really care about rotating things. And at this point, we want to get the state correct. So integer computed self state will be equal to computed cell get component of type TA cell, and from here get state. Okay. Correct. So what we want to do now is to actually instantiate a new copied cube, which is going to be a copy of the computed cell. So then what we're going to go game object copied cell is going to be instantiated at computed cell position using computed cell rotation. And we're actually missing what we want to instantiate, which is our CL, our cell prefab. Okay. Let's see if I wrote this correctly. Yes. So copy cell, we're going to instantiate a cell prefab at the computed cell position. Okay. Then we want to set the state to be the same as our computed cell state. So to do that, yeah, we're going to copy cell, get the component of type CA cell, set state has computed cell state, correct? Then copy cell component. Going to say that set computed is equal to true. Okay, so we don't want to keep updating. We want to say, hey, this one is computed, done. Then ideally, we should also should set that this is a child of the layer. So copied cell transform parent is going to be equal to current layer transform. And I think ideally we should also save it in the stack because we might do some analysis. And actually from next week, I'm going to show you how we can do all sorts of really nice analysis on the stack itself. So in here, in I, J, and current height, we're going to save our copied cell. And I think that's it. There's nothing else to do. I hope I didn't mess any of the code. Let's see. Moment of truth. There we go. Very cool. I can see it's working. I think a clever thing would be to hide the layer that is being computed to be actually there at the top. But no matter, it is working. So that's quite cool. Okay, so this guy has finished computing. In my CA grid now, I should have all my layers. Oh no, he's keep computing. Oh well. Quite a lot of cells. We can optimize this a bit further, but for now we can leave it like this. Cool, I think that's all I want to show you for today. I'm gonna send all the scripts I've made from today's class, okay? So you have it as well. Let me stop this. I want to ask you some questions. Okay, cool. So do you understand what I'm trying to do in the in this computation? Like, does it make sense? Is it hard to follow what's happening?
I think it's good. I think from my perspective, I could follow some part, but for the details, maybe I need to review of the coding. But I think the generation is quite good. The result is quite nice.
Yeah, I actually think it's a very interesting computational model as well. I'm gonna disable this one because I think I didn't optimize a bit this, but think computation because it allows you to create quite compelling structures that are based on neighborhood rules, right? Um, I don't know why it gets so slow when it gets to a top layer, but anyway, it is a very nice computation, and we can use this for a lot of things that are quite interesting. And I'm
Yeah,
going
I'm wondering how, like, in what situation this actually can apply with, like, the prototyping with, like, robotic design or.
well, I think a lot of the units in TO Studio, maybe even in Shajai Studio, you have to deal with components that are linked to other components by some rules, right?
Yeah,
And
yeah,
this may be a first step towards understanding the ideas of neighborhoods. So I'm a cell in a grid, and what is my neighborhood around? Now, the rules here are quite random. We're just checking how many neighbors I have, and based on that, I'm turning something on or off. But you can make this a lot more sophisticated. So you can have multiple cell types, right? You can have, if I start to think as an architect, I could have cells that are living rooms and bathrooms and bedrooms. And I can start to connect them based on neighborhood rules, right? So I can say one living room connects to two bedrooms, and the bedroom connects to one bathroom, or something like that. And you can start to use it as a way to think about generating architectural layouts in a 3D stack. And again, it's a first step towards some type of a generative uh, process by which you create neighborhoods. And I'm pretty sure in the studios, all of you will do something quite different and quite unique. So I don't think you're going to use exactly this computational model, but at least it's a start towards understanding how to work with 3D grids, to understand how you can compute neighborhoods and have some rules based on neighborhoods.
yes. Okay, thank you.
Oh, okay, I think let's stop there. It's been quite a long session. I'm gonna upload the recording after the call, and also the files we developed today, the whole Unity file. And you can play with this as well. Okay?
Okay, okay, thanks.
Cool, guys. Okay, have a good day and have a good weekend as well.
Okay, you too. Thanks.
Thank you.